introducing me. So I would like to thank Professor Yao and the organizers of this conference for the invitation. So I have had a long relationship with Journal of Differential Geometry. Actually, I think I published my first paper in '93 about the Fujita conjecture, so question of uniform generation of adjoint line bundles in projective geometry. But actually, I'm also a complex analyst, and the proof of that result is based essentially on a theorem by Professor Yao on the existence of solutions of Jean-Pierre equations for the zero-Ricci case. And so it's a great pleasure for me to participate to this conference. I published also a second paper later in around 2002, and I think I've been a referee several times, so I'm very glad to celebrate the 50th birthday. So in this conference, I will speak on something different. Actually, a joint work with Junyan Cao and Shinichi Matsumura on L2 extension theorems for sections of adjoint line bundles, or possibly cohomology classes of a higher degree. So you see here the related references. So the first paper already appeared, and also the joint paper which appeared a few weeks ago. And everything that I will lecture about, of course, is also heavily related to the fundamental extension result that was proved by Takeo Osawa and Takegoshi in 1987, with later refinements by Osawa. Although it is an analytic statement that is expressed in terms of L2 estimates, it is surprising that it has many, many applications to algebraic geometry. I can mention one of them. For instance, if you take a projective morphism onto a base S that you assume to be irreducible, then the plurigenera of X are constant. So you assume the family is, say, smooth. To simplify, then this implies that if you look at the plurigenera of the fibers, then this doesn't depend on T. So this is a fundamental result that was proved by Professor Yung-Chong Hsu in 2000. And then the proof was refined by Mihai Paun around 2004. And surprisingly, the only known proof in the general case relies on the L2 extension theorem. And it is absolutely crucial to have the L2 estimate with a very effective constant. So there is no algebraic proof known, in particular, of this purely algebraic result. This is why the extension theorem, I believe, is very useful. Also, my hope is that it will be useful to study, for instance, the abundance conjecture. It's quite related to a talk given by Kosha Birkar yesterday. So now let me enter into the matters. So you take X omega to be a possibly non-compact n-dimensional Kähler manifold, and J in the structure sheaf a coherent ideal. Y, it's zero variety, and you put the structure sheaf on Y to be OY equal OX divided by J. So here, Y may be non-reduced, so OY has nilpotent elements, possibly. And now you take a Hermitian holomorphic line bundle L with a Hermitian metric HL, and you consider the curvature form, theta LHL, equals IDD bar log of HL minus 1. Here we allow singular metrics. So this means that HL is equal to exponential of minus a weight phi. And you don't assume much on phi. It can be essentially any locally integrable function. And then you can compute the curvature in the sense of currents. Well, of course, here we are going to assume in general some positivity. So phi will be locally a plurisubharmonic function. Now, the basic problem is to find conditions on x, y, so especially the ideal J, and the Hermitian metric L, so that for the adjoint bundle Kx tensor L, the restriction morphism from the Q cohomology group on X to the corresponding Q cohomology group on Y. So this is also, of course, HQ of X into OX Kx tensor L tensor OX divided by J. So you ask whether this map is a surjective morphism. Okay, so now I come to the assumptions that are needed. So first, we will require X to be holomorphically convex. So in other terms, by the Cartan-Reymert reduction theorem, this is the same as saying that X admits a proper holomorphic map onto a Stein complex space S. And then a basic observation we will use is that the cohomology of any coherent sheaf on such a space X is always Hausdorff. So the cohomology groups HQ of XF are Hausdorff with respect to their natural topology, which you can take to be the topology of local uniform convergence of holomorphic Čech cochains. And the proof is very simple. You just use the Leray spectral sequence, and you can express these cohomology groups as the sections on S of the direct image sheaves, which you know to be coherent. And therefore, you get Frechet spaces. And therefore, they are Hausdorff. And now, as a corollary, that will be the property that I'm going to use. If you want to solve a d-bar equation, d bar u equal v, on a holomorphically convex manifold, then, in fact, it is enough to solve it only approximately. So d bar u epsilon equal v plus some error term w epsilon, which goes to 0 as the parameter epsilon goes to 0, because, in fact, this equality shows that v is in the closure of the coboundaries. But because the cohomology is Hausdorff, it's the same as saying that the space of coboundaries is closed in the space of cocycles. And therefore, you conclude that actually you can find another solution, which might not be the limit of u epsilon, which solves your d-bar equation. Okay, now I come to how to define properly the subvariety Y from which we are going to extend the sections. Okay, in fact, it is very convenient to take it to be defined by a multiplier ideal sheaf. So what is a multiplier ideal sheaf? I will tell you in a minute. So you assume psi to have analytic singularities. So in other words, psi is assumed to be a positive constant c times the log of a sum of squares of holomorphic functions locally. So that you have analytic singularities, logarithmic poles, and then you add random smooth function locally on your manifold. And then I of exponential minus psi is the sheaf in OX, so-called multiple ideal sheaf introduced by Nadel. That is the sheaf of germs of holomorphic functions at any point x0, such that there exists a neighborhood U on which the function f is locally L2 with respect to the weight exponential minus psi. And then it is always true, proved by Nadel, that such a multiplier ideal sheaf is always a coherent sheaf for any plurisubharmonic function psi. It has additional properties. For instance, it's always an integrally closed ideal, so you don't get all coherent subsheaves or structure sheaf, but you get many, many of them. But there are further restrictions. Of course, you can get a lot of multiplicity. So if you increase the singularities of psi, you get a deeper ideal with larger multiplicities. So if you take n times psi, you will increase the multiplicities. And a typical choice of such weight psi is, again, something of that type. So a constant times the log of square of a section of some vector bundle or sheaf with respect to some Hermitian metric. Okay, so these are the assumptions. The simplest case is when you have the subvariety y, which is actually an effective simple normal crossing divisor, and the corresponding structure sheaf OY. And then in that case, you can take psi to have divisorial singularities. So you take sum of Cj log of sigma Yj for some metric Hj, and Cj positive real numbers with integer parts equal to Mj. And then it's very easy to compute in that case that you precisely get the sheaf of functions that vanish according to the integral part of the divisor. And IDD bar psi in that case by the Leland Poincaré equation is just given by the current of integration on the cycle minus the sum of the curvature forms of your matrix Hj. In fact, the divisorial case is enough to treat the general situation because you can use Hironaka's theorem and you can use a log resolution and then convert by blowing up any higher codimension subvariety to the divisorial case by blowing up. Okay, so now I'm ready to state the main results. So this is a joint work with Junyan Sao and Shinichi Matsumura. So in this form, it's a very recent result. So you take x omega to be scalar and holomorphically convex, and take a Hermitian line bundle, HL, and you assume this rather simple double star curvature condition, that the curvature tensor of L with respect to HL plus a little bit more than 1 times IDD bar of psi is semi-positive. So here delta, of course you are on a non-compact manifold, so you take delta to be a possibly a positive function that can possibly decay at infinity. So you don't need any uniform bound. And alpha takes values 0 or 1. So in other words, you need this to be 1 or something slightly larger than 1. So you need 2 conditions. Okay. And then what you expect holds true. In other words, if you look at the inclusion of ideal sheaves given by HL exponential minus phi and HL, so both can be singulars, then the corresponding morphism in cohomology at the HQ level is injective for every Q, including 0. Well, of course, you can turn this also into a surjectivity result because you're going to use the obvious exact sequence. So this is a smaller ideal, so you take it to be included in HL. And here you take the quotient of the ideals. And then you twist this by the invertible sheaf Kx tensor L. And you take corresponding cohomology groups. So, of course, if you know that one map is injective, you know that the other is surjective. The two statements are equivalent. Well, one interesting case is when the metric HL is smooth. So in that case, if the metric HL is smooth, then here you get no condition. So if HL is smooth, so this is just OX. So then you exactly get the result that you expected from the start, namely that the restriction morphism from the group of all cohomology classes degree Q into Kx tensor L restricted to Y is surjective. Okay, so this is essentially what I said. And of course, there is a stronger property. So if you want that map here at the cohomology level to be surjective here in HQ, of course, you would need that the next group which is HQ plus 1 x into Kx tensor L tensor the ideal of HL exponential minus psi, this one is equal to 0. So, of course, if you have this group equal to 0, the result follows very easily. But such vanishing, of course, in general, you can get only by assuming a strict positivity condition. So if you have such a strict positivity condition, then by applying Nadel's vanishing theorem, you can get that this group, HQ plus 1, is 0 and for all Qs. And then you conclude both injectivity and surjectivity. However, this is precisely what I want to avoid, because you want to deal with situations where you have absolutely no strict positivity. You want to deal with morphisms when you pull back some bundles from a base change, or you have a variation of structure, or you have Calabi-Yau manifolds, for instance, where you don't have any strict positivity of the canonical bundle. So you want to study the minimal model program or the abundance conjecture on manifolds which you don't assume to be of general type, so you have absolutely no strict positivity at hand. And therefore, you absolutely want to avoid any strict positivity like this. In that case, it's very easy to give examples where the cohomology groups don't vanish. So if the cohomology groups don't vanish, it's not an obstacle to the injectivity and surjectivity of the remaining morphisms. And precisely, it turns out that without any strict positivity assumption, you can still obtain these injectivity and surjectivity results. And I'm going to explain how you can do that. Let me first state a purely algebraic corollary. So it's just a special case. So you take, in that case, y to be an integral effective divisor. Well, say simple normal crossing. And then you assume as Q divisors this condition that when delta is 0 or a small number, delta 0, so you need two conditions again, then the difference L minus 1 plus delta times this divisor where the integral parts of Cj is equal to Mj is semi-positive. So semi-positive, unfortunately, doesn't translate into an algebraic condition. So a sufficient algebraic condition is that it is the sum of a semi-ample divisor G delta and a flat divisor, pic 0 divisor U delta. So if you have such a relation, then actually the restriction morphism is surjective. And now this is purely algebraic, but I don't know of any algebraic proof at this point. So now I come to the technique. So the technique is based on a twisted Bochner-Kodaira-Nakano inequality that was first introduced by Ozawa and Takegoshi. So it's very similar to the standard Bochner-Kodaira technique, but you twist by two functions, eta and lambda, that you assume to be strictly positive, and you multiply the operators by square roots of those weights. And then you get this inequality here that I will not make a calculation, of course, with some curvature term, B, P, Q, L, HL, omega, eta, lambda. So it depends on all the data. And the expression here is given at the bottom. So it's, oh, sorry, it's here. It should be L instead of E. And then the curvature tensor is multiplied by eta, but then eta comes negatively as well in terms of I dd bar eta, and d eta wedge d bar eta. And lambda omega is the usual Lefschetz operator. And as a result, this thing here is a Hermitian operator on the space of PQ forms with values in L. And this holds true for all compactly supported, say, smooth sections on X. And from that, by using the standard L2 techniques developed by Homander, Kohn, and well, Kodaira, and all those people, then you get the following main L2 estimate. But here, the statement differs in the sense that I will give instead an approximate L2 existence. And it's very important because you don't assume that the curvature B is strictly positive. So usually when you have L2 estimates, you need a strict condition on the curvature. But here you don't have, because you may even assume that the curvature is 0. So since B can be 0, the only way you can manage this is to add a little bit of positivity in terms of epsilon. So if I come back to the previous thing here, because you don't have any positivity here, you just add epsilon u square here. So it may look artificial. But if you do that and apply the L2 techniques, it will solve the d bar with a small error. So now you want to solve an equation d bar u equal v. So you assume that you have a d bar closed form v, and you assume that v satisfies this L2 condition when you apply the inverse of the operator. Of course, it's invertible because you have added this positive epsilon. Okay, then there exists an approximate solution of the d bar equation. So d bar u epsilon equal v plus an error term w epsilon. So this is valid for forms of type NQ, so only for a p equal to the dimension of the manifold X. And then you get the following L2 estimate. So these are your twisting factors eta and lambda, which come with eta plus lambda minus 1. And you have the L2 norm of u epsilon square with this weight, integrated with the Keller volume element on X, plus now the error term. The error term is w epsilon. And the interesting thing is that the error term here has a weight by the adjunction technique, comes with a weight 1 over epsilon. Okay? And then this is bounded precisely by m epsilon. And then, of course, you are going to take epsilon to go to 0. And what happens sometimes, frequently, is that you cannot get any bound on the solution u epsilon. So contrary to what happens in the strictly positive case, you may completely lose control on the solution. However, because of this 1 over epsilon, and the fact that this is larger than epsilon, the error term remains bounded. And if you analyze B more detailed, you may be able to show that the error term goes to 0. So it's a somewhat surprising use of the L2 estimate in which you completely lose control on the solution, but you are able to show that the error goes to 0. So this will be the strategy. And as I explained at the beginning, this is enough. If you know that the cohomology is Hausdorff, this is enough to conclude that you have a solution, but maybe not the limit of u epsilon. Another one. Okay, so now let me enter a little bit more into the details. So, okay. So you take a cohomology class in the quotient of the ideals of any degree q. You can represent this cohomology class by a holomorphic Čech q cocycle with respect to a Stein covering U, given by a small Stein open set Ui. So let C I0 I cube is this Čech cocycle. So it's defined on the intersections UI0, etc., UIQ, with values in OX, KX tensor, L tensor, IHL divided by IHL exponential minus psi. And then by standard sheaf isomorphisms of Dolbeault cohomology with Čech cohomology, this class can be represented by a smooth NQ form, F, which is the sum of the cocycle elements times derivatives of a partition of unity. So you take a partition of unity rho I, subordinate to your covering ui. This is a standard formula in sheaf theory that gives you the form corresponding to a Čech cocycle. And you can view this thing actually, well, the point is that this is in a quotient ideal. So this quotient ideal actually corresponds to the variety defined by the colon ideal sheaf. So you take the multipliers that send I of h into this, and you take the zero variety, so it's not exactly what you would expect. Anyway. Okay, and now you extend this. So extending this means that, so you are in the quotient ideal here, and now you lift your cocycles, Ci0, Iq, you lift them from here to here into I of HL. And so it means that you lift them from the intersection with Y to the intersection of the open sets in X. So let C twiddle I0, Iq be these extensions, and then you take the same formula, and now you get an NQ form, which is with values in this ideal, and defined on X now. But of course, it's no longer D bar closed because of the extension. It was D bar closed on Y, but because you extend by partition of unity, or in a random way, there is no reason it should be D bar closed on X. Okay, so you are going to solve a D bar equation to make a thing now D bar closed. So you do this by selecting a tubular neighborhood, which is defined by your weight psi. So of course you have the variety Y here, and your psi, so you have the real numbers here, and your psi has a pole here, as a pole, so it goes to minus infinity when you approach Y. Okay, so you have X here. Okay, so now you take a tube corresponding to two levels, T and T plus 1, when T goes to minus infinity. Okay? So now you consider this tube here, well, just over there, which is drawn here in green. And here in red, you have Y. Okay? So you have a tubular neighborhood which has a hole around Y. And then you take a truncation function theta, and you multiply your F twiddle by this truncation function to get something that has now a support in the field tubular neighborhood. Okay, so it has support now between T and T plus 1. Okay, so including the white area, the white part. Okay, and now you want something that is D bar closed. So you are going to solve a D bar equation, D bar of something, equal to D bar of this truncated extension, but you have to accept some error, because you are not able to solve without error. And then it's going to depend on several parameters. So first parameter is T, which is the size of the tubular neighborhood. So you are going to shrink the tubular neighborhood so that it converges to Y. And then you have epsilon, which is related to the error. And then by the previous theorem, you can solve that. Well, in fact, there are two terms. The first involves the derivative of theta. So since you have the derivative of theta, it is 0 on the white part inside. So certainly it will converge. And the second term is given by the extension, and therefore it is now in this ideal because of properties of D bar and Cheresh cohomology. And therefore, it's going to be integrable with respect to the weight HL exponential minus psi. Okay, and then you have to adjust your twisting functions eta and lambda, and so I've given the formulas, but I suppose it will be too long to explain this choice. And then you adjust at the same time as you shrink the tubular neighborhood, you adjust the error in a very precise way, so it should decay as exponential of t, but with an exponent that is slightly larger than 1. And if you do that, then you can solve. You have that the solution is L2, but it will explode probably, many cases, when epsilon goes to 0. But the error term can be shown to go to 0. And therefore, these estimates show that you have an approximate extension, and by the initial observation, it will yield the extension. So now the question is, so we have a solution that can explode, so can we still have an L2 estimate? The L2 estimate is crucial in some applications to algebraic geometry, for instance, the invariant of plurigenera. So it's still an open question to know if we can get estimates. And the answer is yes, if psi is log canonical. So, usual condition in algebraic geometry. So it means that the ideal sheaf corresponding to slightly weaker singularities is non-existent. So you have the full structure sheaf, OX. And then it turns out that there is a completely intrinsic residue measure that appears in this problem if psi is log canonical. So it was introduced by Ozawa. So it's denoted by dv y, well, in fact, it's the regular part y0 of y with respect to the calorimetric omega and with respect to psi. So it's a positive measure. You define it as follows. So you take a compactly supported continuous function g on y. Okay, so you have x here and y here. So you want to define a measure on y. So to define a measure on y, you take a continuous function with compact support, here g. But of course, you're going to define it from the tubular neighborhoods. So you need to extend your continuous function on a neighborhood in X, G twiddle. And then you integrate with respect to the weight exponential minus psi. But because it is log canonical, it's just the critical exponent of convergence, which means that if you integrate on that tube, actually you can show that there exists a limit. Well, in general, you have to use Hironaka's desingularization theorem and convert the problem to a case of divisorial singularities, and then by Hironaka, you can show that the limit actually exists and is unique. It's a very simple calculation. And then you get a positive measure. It's completely uniquely defined. And then the theorem is that if your data are integrable with respect to this residue measure, so if you assume that the section F, well, I'm assuming the holomorphic case here, H0. So if you take a section of holomorphic section, which is L2 with respect to this residue measure, then you can actually extend. So here you have a related weight, which expresses the singularities. And then you have, well, a technological constant 34 that is certainly not optimal here. actually, it's important in some cases to have the optimal constant. And the optimal constant was recently obtained by Guan and Zhou in a slightly less generality. I guess that you can get the optimal constant here as well. So it's possible to get the optimal constant. Okay, so this is in the log canonical case. So now if psi is not log canonical, there's still one case where it works. So you consider the successive jumps. So you consider HL times exponential minus m psi. And for a discrete set of values of m, the ideal will jump. So by the Noetherian property, it can be only a set of discrete jumps. And then you look at the successive jumps that are just below 1. You have mp minus 1, and then mp, which is the last one before 1. And then you assume that your section actually vanishes exactly at the previous multiplicity given by the jumps. And then there's still some sort of higher multiplicity residue measure, which again is unique, which is defined exactly in the same way, but you have to take into account this vanishing. So in that case, this thing is not a measure. It's some sort of quotient distribution that becomes a measure only after you multiply by f squared. So you have some sort of higher residue. But the product by f squared is a measure now. It's still unique. And now, in that case, you again get a global extension f2 and it satisfies the very similar L2 estimate. So I will not repeat this estimate. Okay, so I will conclude here by thanking you for your attention and showing some sort of picture of a Calabi-Yau manifold, which is one of the instances where the extension theorem could be useful to study abundance, which is still not known in that case. So I'll stop here.